I'm Joel Brock, and I'm the director of CHESS, the Cornell High Energy Synchrotron Source.
My name's Tim Bunning. I am the Chief Technology Officer here at AFRL.
I'm Kelly Nygren. I'm a staff scientist at CHESS, and I specialize in structural materials and diffraction techniques.
My name is Rich Vaya. I'm the Chief Scientist of the Materials and Manufacturing Directorate of AFRL.
I'm Arthur Wall, and I'm the Director of the Materials Solutions Network at CHESS, or MSN-C.
My name is Luisa Semeska. I'm a staff scientist at CHESS. My responsibility at MSN-C is to run the functional materials beamline.
So I'm Matt Miller. I'm faculty member in mechanical and aerospace engineering. I'm the PI of MSN-C, and I'm also associate director of CHESS.
CHESS is the coolest place on earth. In essence, we provide X-rays to characterize pretty much anything on length scales ranging from the separation of atoms, the size of a plant, or say the rotor on a turbine in a jet engine.
Probably a few sites in the world that can do this sort of imaging. The uniqueness comes from the flux of the X-ray radiation, so the intensity, if you will, of the X-ray radiation. It allows you to do things that you can't do with a conventional X-ray source. So here within AFRL, we have numerous X-ray sources. They're fixed sources. We stick samples in them. We do an exposure, like if you break your leg and you have an X-ray done. Those exposures are defined by the length of time you need to expose, which is dependent on the material, the condition, depending on the X-ray machine.
Also, we can perform time resolve type measurements. We take our materials and we can either process materials and look at the material as it's being processed. We can do standard mechanical tests on a material, such as tension, torsion, fatigue, look at the microstructure of that material as it evolves in real time. And we can also do experiments as quickly as on the nanosecond scale, so we can look at parts as they respond to high impacts. The partnership that AFRL provides cultivates this wonderful atmosphere of exciting scientific problems that they bring to us from across the defense, and then bringing together all these experts to be able to solve really meaningful problems. And this is really exciting because in addition to the nature of these problems, with the support that we have from AFRL, it really pushes the facility to be innovative, to go after automation, to go after more ambitious types of problems and techniques. And I think just push us and springboard us even further into the future, but also make sure we're grounded in very meaningful science and meaningful applications.
So that's one of the novel things about our partnership with Cornell and the CHESS facility, is that we've been able to install capabilities within what's called a beamline, or where the X-rays and the energy come out, that it actually can handle large pieces. There's large robots that can manipulate large structures like turbine blades and rotate them around and move them around within the beam, so you can get spatial information from the root to the edge of a turbine blade, for example.
The current partnership between AFRL and CHESS, which is embodied in MSN-C, is a very symbiotic relationship. It's helpful in both ways. From CHESS's point of view, the partnership with AFRL, of course, provides funding, but even more importantly, provides access to real problems, challenges that are faced by manufacturing industries, and access to those manufacturers. So that's one of the things that CHESS gets from the partnership. What AFRL gets is access to these almost unique resources, state-of-the-art tools for addressing real problems facing AFRL and manufacturers every day.
Yeah, so one project that really illustrates the close relationship between AFRL and MSN-C is the development of the 3D printing setup at the functional materials beamline. This was a project that involved designing a whole 3D print setup around a commercial print head. They actually took apart their printer and sent us the head. We built the printing setup around that so that it could work in the beamline.
I think it's a bright future, and based on a lot of the momentum that we have already in terms of the domain science, and you know, you get people used to making these kinds of characterization measurements, and get them used to coming to a light source to make that, and uncovering new science and uncovering new ways of making engineering decisions. There's stuff to do at both ends of and what better place to make those kinds of advances? You know, I'm a little biased, but how could it be any place better than Cornell?